In this video, we'll discuss mutable state and the assignment operator. So up until now, we've said that Scheme does not support assignment, just bindings. So we had the ability to create a binding between a name and a value, but that binding was not mutable. Once it was created, we said it could never be changed. It could be destroyed and replaced, but that binding itself essentially always stayed the same, or was a constant. Another way of saying this is that Scheme is referentially transparent. So referential transparency means that a user of a language doesn't need to know how the bindings of that language are stored. They're essentially invisible to the user. The user just sees a binding between a name and a value, and they can associate that name with that specific value throughout the entire body of the code. Another way of saying this is that an expression is referentially transparent if it can be replaced with its value without changing the behavior of the program in which it resides. And this is exactly the knowledge that we've been using in order to walk through all of our expressions with the substitution model. We take an expression, let's say the body of some function, and we substitute the values of the arguments for the symbols of the parameters throughout that entire expression. And once we do that, we can then reduce and simplify the expression down to a single value. So, by contrast, if a language allows assignment, then we have to consider bindings as being not just between a name and a value, but between a name and a memory location, because the value in that location might change over time. So languages with mutable state are considered not referentially transparent. These are typically imperative languages. So in this video, we're going to remove referential transparency from Scheme and allow for mutable state via the assignment operator. So the assignment operator in Scheme is what's known as set. So the syntax is here. It's a special form, set exclamation mark. The exclamation mark is a bit of a naming convention. So any function that ends with an exclamation mark is used to mutate an existing binding. So it has some sort of mutation or side effect to its operation. So Scheme is not a purely functional language. It does support some imperative features like this assignment operation. So set works as follows. We have the keyword set exclamation, some symbol, and then some value to change it to. Much like define with some name and value, but in this case we're mutating an existing binding rather than creating a new one. So for example, let's create a piece of code here. I could say define x to be 1 and ask what's the value of x, and it's 1. And then I can say set x to be 2. And then ask what's the value of x, and it now has the value 2. So set changes an existing binding once it's already there. So this is a special form because it's used for its effect, not its value. Notice when we typed in set x2, we didn't get a result. There was no value for that expression. It just changed the value associated with the symbol x. It's also worth pointing out that the variable must already exist. For example, if I were to set y to be 3, the variable y doesn't yet exist, and we get this error, assignment disallowed, cannot set undefined, because this variable doesn't exist. If we define it first, then we can set it, but we can't just set an unexisting variable. So a lot of languages will use equals for both of these things, for creating a binding as well as for mutating a binding. In Scheme, we have two separate operations, define for constructing that binding, and set for changing it. All right, so you might be thinking, well, what's the difference between define and set? Why use set at all? Why not just create a brand new binding every time we need to change the value associated with the symbol? What's the big difference? So let's see a simple example that hopefully will illustrate that. So up in the definitions area here, define x to be 0, define y to be 3, and then I'm going to define two functions, one for binding two values, so bind example, which will say define x to be plus y 100, and then return the value of x. So a real simple function that creates a local variable x, sets its value, and returns that value. And a similar function, assign eg, that does the same thing but with set. So set x to be plus y 100, and then return the value of x. So both of these functions look pretty similar. The only key difference is the word define versus the word set. So let's see what happens. So first off, the value of x starts off as 0. That's this global variable x that we've constructed here. Now, if we run bind eg, something like bind eg here. So walking through this, it creates a local variable x and sets its value to y plus 100. Now, there's no local variable y here, so it uses the free variable y, which has the value 3. So plus 3, 100 gives us 103. We set that into this new local variable and return that value. So we get 103 as our output. But if we ask what's the value of x, x hasn't changed. This global variable x hasn't been altered at all. But if we run assign EG, we get the same answer. So it says set x to be plus y 100, and y is still not a local variable, so it uses the value of y out here. So we get 3 plus 100 for 103. And then we say set x. Well, as we've seen, set only works if a binding already exists. And there's no local binding for x, so we go looking into the enclosing scope, and we change the x in the global scope. So now if we ask what is the value of x, it has changed to 103. So while the bind.eg created a local variable hiding that global variable, set in this case mutates any binding that it can find. Okay, so it doesn't create a new binding to hide it. It just says access which one I can see and change that one. All right. Worth mentioning here as well, there's additional assignment operations when you're dealing with lists. There's set car and set CDR. So if I define a list to be 1, 2, 3, 4, there's my list L. I can say set the car of L, so set car exclamation, and I'm going to set that to being a 0. And if I ask what's the value of L now, it is mutated so that the head of that first pair, or the car of that first pair, now points to the integer 0. Similarly, I can set CDR of L to be the list 20, 30, 40. And now what this does is it takes the CDR of that first pair and changes what that points to. So I created a brand new list here, a separate space in memory, and this set CDR goes into L, which remember is actually just a pointer to that first pair in the list. And that says change the CDR of that pointer to now refer to this new list. So it says the car still points at 0, and the CDR points at 20, 30, 40. So we can mutate lists as well as individual variables. All right, so there's some good and bad to having assignment in a language. It supports an imperative style of programming. So let's first look at an example of that before we talk about pros and cons of it. There's actually code right here. We'll just use this. So starting with this functional example. So we've already seen this code here. Let's copy it in here. So this computes a factorial of a given number based on an iterative process. So we have our outside function, factorial n takes in whatever value of n, and our inner function, which has helper values, our inner helper function, which has temporary values for our working total and a counter for how far along in the process we are. We start both of those at 1, and then each time through the loop, we multiply the current value of counter into our running total, and then increment counter by 1. So just 1 times 2 times 3 times 4, all the way up until we finally pass n, and then we return that running total as its final value. So this is an example of a functional style piece of code. Now, again, notice if we're assuming referential transparency in our language, we have the ability to change values through time still. We have a process of this running total building over time, but notice it's not changing an existing variable when it makes those changes. Each time we make a change to that running total, we're actually creating a brand new variable, a brand new environment, and a brand new variable, because we're calling a new function each time. So we're saying create a new scope, a new activation record that has storage for a product and counter, and set the value of that new product to the old product times counter. So it creates a brand new space, a brand new binding with a brand new value. Even though it happens to have the same name, we have many different activation records, so we're storing separate instances of this variable. Consider, on the other hand, an example of imperative style programming for this same problem. Let's take this code and walk through it. So factorial now, again, we have this public function that says take in some value n, and this works very similarly. It's still using a sort of iterative process, or a process similar to what we would use in a loop. So we're going to start at 1 and multiply 1 times 2 times 3 times 4. The difference here, though, is that we'll have sort of external variables, not quite global, but outside of the helper function. So there'll be free variables inside the helper function, which means they're going to persist outside of the individual instances of this loop. Right? One call to iterate will access product and counter, and then start a new call to iterate, which will still be inside this outer environment where the exact same product and counter variables will still exist. So because of that, we don't need helper variables here. We don't need a temporary product and counter for each time we iterate through this iterate function. We're just going to use these free variables and use set in order to mutate them once per iteration. So to walk through this, we start iterate with the values 1 and 1 as our product and counter, and then we mutate them. So we set the product to counter times product, and we increment the counter by 1, and those are both mutating these free variables outside of iterate, and then we call iterate to repeat. So we go back up to the top, and we do that multiplication and addition again, right up until our counter reaches our base case, at which point we can return the value of that free variable. So it's still computing factorial, and it's still using a sort of iterative recursion. Just now we don't need to have separate instances of those variables for each separate iteration. We can use persistent changing free variables instead of these new copies each time. One thing to point out is that set is often used inside of a begin statement. The reason being, as I mentioned when I first taught the begin statement, is that set is only really used for its side effect, and begin is typically used when we have some sort of side effects like displays or now like the mutations of variables. So because set doesn't actually have a value, typically speaking, it's going to be used as part of a begin statement followed by something that does have a value. In this case, the call to iterate, which will eventually return the final value of product. Right? If we had set as the last line here, then the entire function factorial wouldn't have any result. All right, so it's a bit of side effect programming as one way of describing this iterative style as well. Now, one thing to point out about this iterative design is that the order of these two set lines is very important. So think, what would happen if I reversed these two things? If I took this set and put it down here. Well, actually, first let's run it first to make sure it all works properly. So the factorial of 5 should be 120. Factorial of 10, I don't even remember, some large number. Okay, let's actually, factorial of 6 should be 120 times 6, and that's about right. Okay. So what we can do now is, what would happen if these two values were reversed? Or sorry, these two set operations were reversed. So first we're going to set the counter to counter plus 1, and then we'll set the product to product times counter. If we run our code, factorial of 5 again, and now we get 720, which we just saw was the factorial of 6. And similarly, if I say factorial of 6, we should get the factorial for the next value. So in this case, it doesn't have a catastrophic result. In this case, our numbers are just a little bit off, but you can see that our code is highly dependent on the order of these operations. Whereas before, it doesn't really matter if I put product or counter in either order in the parameter list here. In this case, the order of these operations needs to be done one before the other, otherwise we'll run into some sort of error. Right, so now when we're dealing with mutable variables, we have to give consideration that each line is using the correct version of that variable. Okay? In pure functional programming, where we have referential transparency, this isn't an issue. If we have a variable, it's going to be the same value no matter where we refer to it, so we don't really have to worry about different versions of that variable. If we have mutable values, now these variables are changing through time, so we have to worry about these different versions. All right. So there's some advantages to introducing assignment into our language. Imperative descriptions are sometimes more natural, especially if that's the sort of language you've been trained to program in, such as CS students at Carleton University. So it's a way of referring to problems or solving problems that's more natural or more readily available to many thinkers. It also models the machine a bit more directly as well, so it has the ability to be more efficient in that regard as well. We'll see later that having assignment in our language also enables encapsulation and object-oriented programming in the language, which is an important design principle in developing large modular systems. But it also adds the ability to reference time in our program. We can create more complex expressions that have time-varying behavior. Can, for example, create a function that returns one value in a first call, and then if a second call with identical parameters is provided, we can get a different value just because of these side effects or these changing parameters through time. So, for example, you create a function that counts the number of times that function has been called. Now, that's all great and all. It's the ability to increase our expressive power. However, with that increased expressiveness comes the complexity along with it. So some cons in terms of introducing assignment to our language, as the compiler, the interpreter, can no longer optimize the code with pure functional assumptions. So side effect free programming is a very easy optimization to perform. So if a language has referential transparency, it provides a lot of leeway for the interpreter to decide where to store values, how long to keep them around, things like that. So the flow of the values through a program will be visible to the compiler because they're not changing over time. Once we have mutable variables, the compiler can't really do that without actually running the code. So it can no longer optimize based on just the textual description of the code itself. This also means that the code is susceptible to new bugs, especially when we're dealing with shared mutable variables that are being accessed from different parts of our program, or particularly if they're being accessed in asynchronous environments. We now have to worry about deadlocks and race conditions and all those if we have multiple threads or processes running. And finally, we can no longer use the substitution model to describe our programs. If we have mutable data, that is to say, if we don't have referential transparency, we can no longer accurately model the process or the steps of our process just using substitution. Set adds a sort of ambiguity to the meaning of different symbols, which means that the substitution process can no longer rely on that referential transparency to provide an accurate depiction of the resolution of our expressions. So let's see that actually. So set breaks the substitution model. Let's see an example of a simple piece of code where we can see that clearly. So define simple increment function. And this is just going to do two things. Begin, it's going to say set x to be plus x1, and then return the value of x. And that's it. So if I said, let's run our code here. Parts after keyword set counter. Oh, I put a space in there. Oops. All right, try that again. So if I said increment 3, for example, it returns 4. So the code seems to work fine. But what happens in the substitution model for this example? If I said incr 3, so substitution model, again, we walk through eval apply and then substitute. So we evaluate the sub-expressions. That's a function reference and an integer, so it's about as simple as we care to represent them. So the next step is to replace that with the body of the function and substitute. So we have begin set x to be plus x1 and x. Now, set's a special form, so this here is referring to a symbol, whereas this one is referring to the value. So when we're changing x, we can ignore that first one, but we change this to 3 and this to 3. And now we walk through the body of this. So begin says first evaluate this expression. That does a set. Now sets don't really get represented in the substitution model, in part because they break the substitution model, but also in part because they don't have a value. So essentially what happens next is that gets evaluated, some change occurs, but not in our substitution model, and then we're left with the remainder of that line, which is just the value 3. Now we shouldn't have a 3 here because as we already seen when we run the code, we get 4 as the answer. But this 3 comes in because we did substitution for this argument 3 for the parameter x throughout the entire body of the function at the outset. So the substitution model, assuming referential transparency, says put this 3 everywhere I see an x, and then I'm done, and then evaluate. But because the body of this function involved a change of state, a mutation, the set operation, this instance of x should have been turned into a 3, but this instance of x refers to a different version of x. It's a version after assignment, which should have been 4. All of which is to say the substitution model doesn't work once we allow assignment into our language, so we're going to need a new model. And that will be the subject of the next video.